like to introduce our next speaker, Olivia Weaver. She has been with Hedin Environmental for 3 years as a geologist. So with that, please welcome Olivia.
Thanks. All right, thank you guys. I am gonna just do some quick background on Hedin and myself. So, as she said, I work for Hedin Environmental, and we're a small consulting company. We specialize in passive treatment of mine water, and we use a variety of different passive methods to do this. But over the years, we've installed 100 systems around the world, but mostly in Pennsylvania. As well as 17 drainable limestone beds, which were installed since 2019, which is mainly what I'm going to be talking about today, are drainable limestone beds. And as for myself, I've been with Hedin Environmental for 3 years as a geologist, and I do a lot of work with investigating discharges and characterizing watersheds, as well as treatment systems and figuring out conceptual design. But today, I'm going to be looking more at limestone beds and different ways we can characterize their performance, and some methods that we've developed for looking at the effectiveness of maintenance activities, as well as just overall characterizing how well the beds are performing. So just some background for those that don't know on what is a oxic limestone bed. So this is just an open bed of limestone aggregate. As you can see in the pictures, I have 2 examples of 2 different sites. And there's no cone post on top, it's just open to the atmosphere. And we use it to raise the pH, remove metals, and generate alkalinity. And of course, as the bed is removing metals, these metals are deposited in the bed, so then the stone will foul and accumulate metals. So that's one of the problems that we have with OLBs. The limestone will foul from these metal solids, and it can be from iron, aluminum, and sometimes manganese solids. And as these solids accumulate in the bed, this will degrade the performance. So it will remove less metals, and it will not generate as much alkalinity. And the solids can be in a form of either a scaling on the surface of the stone or a sludge that is on top of the stone. So the scaling will prevent the water from interacting with the surface of the stone, and then the sludge, as it sits on top of the stone, prevents the water from getting into the pores of the aggregate. So all of this is leading up to the metals are accumulating in the stone, so we're eventually going to have to clean the stone. One way we try to manage these solids is by draining the bed. So we can drain the bed. Usually we do it weekly, or after 1 bed volume, we'll drain the bed empty and let it refill to try to mobilize some of those solids and carry them out of the bed. And we can do this either manually with a valve or with an automatic flushing system called a smart drainage system that has a solar panel, and we can schedule it to flush at certain times. But either way, eventually the stone gets to a point where we're going to have to clean it because there's too many solids that have accumulated in it. So we just finished up a project looking at what is the best way to clean the stone. So this was with the Western Pennsylvania Conservancy. We were the technical consultants, and we looked at different cleaning techniques and developed a best management practice from this. So a lot of the work that I talk through with this presentation is from that project, and then some other stuff that we've done after that. So I'm going to go through we tested 4 different cleaning methods as a part of this project. So the first one being stir and rinse, and you can see, find my mouse. There it is. So you can see up here in this picture, stir and rinse is where we will mix the stone with the excavator, and someone will be spraying water on the stone as it's being mixed. And then the solids will be dislodged from the stone and be carried away from the water through the effluent plumbing of the OLB. And then dozer method, I have a picture of an example down here, the second cleaning method. So with this, the dozer will push the stone out of the bed through standing water, and you lower the water level as you're doing this. So the stone is rolling in the water as it's being pushed and solids are being dislodged from it. And then eventually the solids that are being dislodged in the water, again, kind of with a stir and rinse, flow out through the effluent plumbing. But with these two methods, not all of the solids are removed. A lot of the solids are still remaining in the bed. Then a third method we looked at was using a screening bucket. So this is a special attachment that goes on an excavator, and there's two different types, one that rotates parallel to the boom and one perpendicular. So with this, you scoop stone into the bucket, and as you can see in the picture, you spin the screen as it's in a wash box and put water on it at the same time. So as it's spinning, solids are dislodging from it, the solids are falling into the wash box, and the importance of the wash box is that it's collecting the solids, which are then pumped out of the bed, so no solids that we're washing off the stone are re-entering the bed. Then the fourth method that we looked at is even more specialized piece of cleaning equipment. So with this one, you need one or more excavators to do this. So in the bottom right corner there, the stone goes into the top of it here with water, and then the stone is rotated in this metal drum. And as it's rotated, the solids are dislodged from the stone and they fall into a metal pan, which is attached on the bottom here of this. So the solids are falling into the metal pan with the water and being pumped away, and then the clean stone goes up and is deposited on the opposite end of it. So again, this is really good at capturing those solids so they're not being deposited back into the bed with this cleaning method. So the four cleaning methods we looked at: mix and rinse, dozer, screening bucket, and trommel. And with these, for the project, we cleaned 36,000 tons of limestone at 18 different passive systems, and we used one of these methods at each of these systems. And this is kind of a summary table going through the unit cost and then the throughput for each of the method and some pros and cons for each. So you can see the mix and rinse and dozer were the cheaper of the methods and had a higher throughput. But the con with these methods is that, like I discussed, the management of the solids, some of these solids are still remaining in the bed. Whereas with the screening bucket and the trommel, while they're more expensive and their throughput is relatively lower, all of the solids are removed from the OLB, which is much better management, so those aren't going back into the bed, and we're able to maximize the amount of space for treatment with stone that can treat the water. But overall, the main difference between these methods was where are the solids going. And so then we were trying to look at what could be a test between how can we compare these methods to see which is better as far as cleaning interval. But based on the timeline of the project, we can't be waiting 5 to 8 years for the stone to foul again. So we were trying to figure out how could we find another way to evaluate the effectiveness of the cleaning besides waiting for how long it took the stone to refoul. And with this, we developed several methods of characterizing the beds before and after cleaning. And that's mainly what I'm going to be talking about. So two simpler methods, which I'm sure most of you are familiar with, we would just gather water quality data going into and out of the bed before and after cleaning, and that included usually iron, aluminum, manganese, and general AMD chemistry. And we also would measure field alkalinity and do alkalinity tests. And then getting into some more complex evaluation methods, we would do porosity tests and tracer tests. So I'm going to go through each of these, and specifically I'm going to focus on porosity and tracer tests. But first, briefly, water quality. So like I said, the goal with the oxic limestone beds is to have them generate alkalinity and also remove metals. So the question we've been trying to answer when we're looking at this is the bed removing metals? And then as far as pre and post cleaning, are we improving the amount of metals that the bed is removing? So just a brief example here of this, I have a site called Fallbrook, and I have on the y-axis metal loadings that are removed in pounds per day, and then pre-cleaning is in the orangey reddish color, and post-cleaning is in blue. So you can see there's quite an increase in metal removal post-cleaning. The aluminum removal increased 55% and manganese increased 21%. So that's what we're wanting to see after we clean these beds. We want to see an improvement in their performance, which was the case that we saw at this particular site. So then alkalinity. We would be measuring alkalinity, leaving the bed before and after cleaning to see, is the alkalinity improving? Are we generating more alkalinity after we clean these beds? And then we'd get into even more detail by doing alkalinity generation tests using ALCAS, which I have pictured here. So these are syringes filled with high calcite limestone, and we would fill them with the raw water, get as much air out of the syringe as possible, let them incubate for 4 to 6 hours, after which we would filter them, measure alkalinity, and this gives us an idea of the maximum amount of alkalinity that the water could be producing when it's in contact with the limestone. So then we would compare these ALCAS values, so the maximum amount of alkalinity it could be producing, to what is the bed actually producing, to then get at, can we be improving the alkalinity generation? So this graph is showing different sites that we tested for the limestone cleaning test, and then on the y-axis is the percent of ALCAS value we achieved. So it would just be the alkalinity we measured divided by the ALCAS value that we got. And then I have before and after cleaning. So again, before cleaning is the orange color and after cleaning is blue. So you can see for most of the sites, we had an increase in alkalinity generation post-cleaning. So for pre-cleaning, an average value for what the sites were achieving is 43% of the ALCAS, and then post-cleaning that increased to 77%. So that was good for us to see that the cleaning is actually helping to improve the alkalinity generation in these OLBs. Which then leads me to some more complex methods of trying to get at the effectiveness of the cleaning, one of which being porosity. So generally, when we're thinking about porosity in OLBs, most people assume that the porosity is around the 45% range, but we found as we're doing these tests that a lot of times the actual porosity was much less than that. So as I discussed with OLBs, as they're removing metals and the scaling and sludge accumulates, that decreases the porosity in the bed. And then what we would do is we would measure the porosity before and after cleaning to get at, is the cleaning improving this? So we would do this by emptying the bed and then measuring the water level. So I have an example of a setup here with a water level control structure. I'd install a probe in it to then measure as the water is refilling, and I would take the time it took to refill from the water level, and we would get flows before and after, so I know how much water is coming into the bed. So I have the total amount of water coming in, and then a volume of the bed from as-built, and using all of that to calculate the volume that's being filled by the total volume to then get the porosity of the bed. So here I have an example of a test that we did at Sterrett DLB. So I have water elevation is on the x-axis and then porosity is on the y. So as we do these, you can kind of get even into more detail by looking at what is the porosity at various depths within the bed. So if we look at the porosity of the bed as a whole, that was 30%, but when you break it down using the different water elevations, you can get at a more detailed look of the porosity. And in the case of Sterrett, the bottom foot and a half of the bed had a significantly reduced porosity. So it ranged from 9 to 21%, whereas the rest of the bed is hanging around closer to the average 30 to like 45%. And this was something that we commonly saw in quite a few of the beds when we drained it down far enough to look at the bottom part of the bed usually had a reduced area of porosity. And we're assuming that could be from through the years. Most of these sites weren't newer sites that we were doing. They had been in use for a while. So through the years of maintenance and solid settling, if you aren't removing those solids from the bed, they're eventually settling down to the bottom of it. And we think that could be what's causing this reduced area of porosity in the bottom portion of the bed. So here is an example from porosity tests that I did before and after cleaning. And this site is the Kentucky Hollow in Allegheny County. So you can see pre-cleaning, test is in the blue diamonds, and then we did 2 pre-cleaning tests. So the blue and red diamonds are pre-cleaning. And the porosity with those is hanging around 35, 36%, and alkalinity we're producing 110 milligrams per liter. And then post-cleaning, so like a few weeks to a month after we cleaned the bed, we retested the porosity, and it increased to 45%, and alkalinity generation increased as well. So that was the goal of looking at this, is the cleaning actually improving the porosity of the bed? And in this case, it was. And it also improved the alkalinity generation. So this is a summary showing the sites that for the DLB cleaning project we tested the porosity at. And on average, there was only a slight increase. So there's a 5% increase from the porosity before and after cleaning. And there's a lot of other factors in play here with the cleaning besides just improving the porosity, which is why some of them you don't see much of a difference. But for other sites, there was a pretty significant difference. Like the first one, Skutac, we saw quite a big increase in the porosity. So it just was kind of dependent on the site. But that leads us to the fourth evaluation method that we use to look at these OLBs during the cleaning project, which are tracer tests, which are what I love to do. I love injecting fun fluorescent dye into these beds. But we would do these to measure the hydraulic retention time in the bed. And we used sodium fluorescein dye, which is also known as just fluorescein or uranine. You don't want to look it up in literature. There's a lot of arguments about the naming of it. But and I used a logger probe, so I would install the probe in the effluent box, usually of the system, to measure the dye concentration. And we use fluorescein dye because it's non-toxic, so we don't have to worry about any environmental or health and safety factors with that. But also it photodegrades, so its half-life, I think, is like really short in the sunlight, so you don't have to worry about it hanging around for a long time. It quickly will be photodegraded and gone. But as far as calibration of the sensor, we kind of changed our method as we learned more and did a little more research about it. So initially, I would calibrate the probe using the standard solution bought from the lab, but as we were looking more into it, we realized a better method might be to use the actual mine water that I'm injecting the dye into, and then the stock dye that I'm using to inject for the test itself. And by using that, we're kind of eliminating a few sources of error that could be happening. We found that the dye could be interacting just with the chemicals and the metals in the mine water or the turbidity in the mine water that's affecting the fluorescence that the probe is capturing. So by using the mine water itself, I'm kind of equalizing that. So by using the mine water in the calibration, I'm kind of maintaining whatever error could be there. And also there's a slight possibility that my stock dye that I'm using to inject, the reported concentration could be different from what the concentration actually is. So by maintaining and using the same dye across the calibration and injecting, that's another possible source of error I'm removing. So generally, I would use the mine water itself I was injecting into for the calibration and making my own calibration solution with the dye that I was going to inject with. So there's a lot of different methods if you do any research on how to determine how much dye to inject into the beds. There's a lot of very complicated equations with velocity and flow and length, and we've kind of simplified it to look at what our goal is, especially with these DLBs. We want to look, so we decided to look at the pore volume in the bed, and we calculated how much dye would we need to inject in order to get 10 ppb concentration of the dye in the pore volume of the bed. And then that determined how much dye we would actually inject. So because we were doing tests at different sites and also multiple tests at the same site, we wanted to try to find a way to normalize the data to compare it across these different sites and different tests. And we did this by calculating a theoretical retention time, which generally speaking, we would take the pore volume divided by the flow rate to get at the theoretical retention time. So how long should the water actually be in the bed just based on these factors. And we also normalized the dye recovery, so we were looking at then the effective dye recovery to account for any dye that we're losing. So because I'm injecting a known amount of dye, like I have pictured here, I'm injecting, say, 20 milliliters of dye, and then I'm measuring how much is leaving the bed, I should be able to account for all the dye that I've been injecting, and my dye recovery should be 100%. But as in the case of most things, sometimes we got 100%, but most of the time you're not actually recovering all the dye. You're losing some of the dye. So then we're like, okay, can we figure out why we're not accounting for all of our dye loss, or all of our dye recovery, I should say. Some of the factors that could have been affecting this is just the geometry of the beds. The dye could be isolated in different portions of the bed based on preferential flow through the stone, or it could possibly be from solids and the dye absorbing onto solids within the bed. So our average dye recovery for pre-cleaning test was 26% and post-cleaning was 53%, which I think kind of is indicating there may be some factor with the solids. Presumably there'd be less solids in the bed after cleaning. But to look at this more, I did some bucket tests to try to figure out, could AMD solids be affecting the dye recovery that we're having in these beds? So for the bucket test, I had a control, which was just clean mine water with, I put 10 ppb concentration of the dye into it, and I would let that sit for a half hour. So you can see on the graph I have time on the x-axis and then the dye concentration on the y, and the dashed line is that half hour where then I changed the control. So after a half hour, I would either add clean limestone, or I got fouled limestone from a mine site that had aluminum and some manganese solids mixed in with it. So I would add the clean limestone, and then I added the fouled limestone to see what effect that had on the dye concentration. So you can see the clean limestone I have is the blue line, and after the dashed black line, so after I added it to the control, there was really no change in the dye concentration. Versus when I added the fouled limestone to my control, there definitely was quite a decrease in the dye concentration. So it dropped from the control for the dirty ones were hanging around 10, 10 and a half, and they dropped to like 7 and 6 in that range, and even 5. And they were continuing to decrease until they plateaued a bit. So it definitely seems like there was some interaction between the AMD solids and the concentration of the dye that may have been affecting our low dye recovery rates. So as we were looking at these, then we get to the fun part of, okay, we've done the test, now we need to interpret the data. So we would look at the peak in the dye recovery, which is the dominant flow path. So that is the solid black line showing the peak of the dye. And the solid black line is the percent of the maximum dye concentration. And we also would look at the 50% effective dye recovery, which the effective dye recovery is represented by the dashed line. And like I said, the 50% is the mean flow path, whereas the peak is generally the dominant flow path. And we would compare these two values to the theoretical to get at what is the actual retention time versus how much retention time were we expecting the bed to have. And generally, like, our goal is to have a longer retention time to give the water more time to interact with the stone to generate alkalinity and to remove metals. So I'm going to go through a few examples of these that we did. So for the limestone cleaning test, we had a tracer test that we did before and then after the cleaning. And this is an example of MR4 site. So the pre-cleaning is in orange and post-cleaning is in blue. And you can see I have listed the theoretical retention times and then the peak and the 50%. So for the pre-cleaning, try to point it out here. the pre-cleaning peak was at about 25% of the theoretical, and then the post-cleaning peak was hanging closer to 100% of the theoretical retention time. So we definitely saw an increase in the retention time compared to the theoretical post-cleaning, which was what we're looking for. After we cleaned, we wanted to see an improvement in the retention time. And for most of our sites, that's what we saw. So this is summarizing the percent of theoretical retention time for the tracer test that we did for the limestone cleaning project pre and post cleaning. So for a majority of the sites, the retention time increased, which was what we were looking for as far as the cleaning went. So with these tracer tests, one thing we could use them for, like I was discussing with the limestone cleaning project, we can look at the effectiveness of the cleaning and see if there's any improvements in retention time from cleaning the bed. But they also can help us to diagnose systems that might not be performing as well as we'd want, or we can even compare different OLB designs to each other, especially like I discussed with normalizing the data. That allows us to kind of take tests from different sites and compare it to each other and see what the differences could be. So I'm going to go through a few different designs that are comparing the retention times to each other to see the difference between that. So this is just a cross-section of an OLB in a basic design that we usually design. So the influent in the upper left is represented. So that is like a fountain pipe going across the width of the bed, evenly distributing the flow into the bed. And then the water level is just below the top of the stone, and the effluent is similar to the influent, but at the bottom of the bed, a distributed pipe that has perforation, so there's an even distribution of flow leaving the bed. So this graph is showing a lot of different tests that we did on sites that had that that design with the plumbing. So the x-axis is percent of theoretical retention time, and then the y is the maximum dye concentration. So if we're looking at the peaks, because it's the maximum dye concentration, they range from like 15 to 60%. So we kind of had quite a range as far as achieving the theoretical retention time with beds that have this design. But these were also done with pre and post cleaning, so there's differences with that as well. But if we then look at a different design, so this site is called BBWA 3888 up in Elk County. We're working on a redesign for this site, but we wanted to look at what retention time the site has in the way it's currently designed. So with this, the influent is just a single pipe coming into the bed, and then there's a 1-foot water cap on top of the stone, and the effluent plumbing is 3 perforated pipes that are running the length of the bed, so that is giving us vertical flow out of the bed. And when I did a tracer test here, this test is highlighted in red. You can see the peak compared to the other designs is much lower. So the peak was at 7% of the theoretical retention time, which I think in actual hours, it was like maybe 3 hours that it was in the bed, and it's quite a large limestone bed. So the distribution of flow wasn't quite as well as we would have thought with the water cap on top of the stone. So another site that we did a tracer test on to compare the designs is Puritan, an overflow bed. And the setup of this bed is it has a single pipe in, similar to BBWA, but there's no water cap. So the water level is below the stone, but it does have vertical flow out. So it's a single perforated pipe running the length of the bed. And the results from that is shown in the darker kind of green color. And the peak from that test was 13% of the theoretical. So again, a little bit higher than BBWA, but significantly reduced from what we would expect based on the theoretical. So this is another iteration of a design at Gibson to compare it to all of these. So this site had a single point in that came into the corner of the bed, water level just below the stone, and then distributed flow leaving the bed. And this one is in the light blue color. So the peak of this was 8% of the theoretical retention time, which again, much lower than the other sites for comparison. So it's really interesting when we're doing these tests by like just what I've gone through here, you're really able to compare a wide variety of different sites and different designs of these sites directly to each other to see what effect the plumbing can have on the retention time. So we're seeing like with these sites where the retention time is much shorter, possibly there might be short-circuiting issues with the vertical flow, or there could be preferential flow paths that are causing the retention time to be significantly shorter than, in theory, we would expect it to be. And the tracer test is a good, relatively simple way to get at that and give us actual data for what is the retention time. So generally, like I went through a lot of different methods here, but for this limestone cleaning project, we looked at the water quality and the alkalinity before and after cleaning to give us a good idea of like how many metals is the bed removing, is alkalinity generation increasing, and generally we saw that metal removal was increased after the cleaning and alkalinity usually was increasing as well. And those are good, pretty simple comparisons to get an idea of how well are the OLBs performing and is cleaning the bed improving the performance of the bed. And then looking at more complex methods of evaluating these limestone beds, we get to porosity tests. So they can give us an idea of areas of reduced porosity. Like I said, a lot of the tests that we did had reduced porosity in the bottom foot and a half of the bed. And then tracer test, there's a lot of different data we can interpret from this, and we can define the effectiveness of cleaning and maintenance like we did with the limestone cleaning test by doing these tests before and after cleaning to see if we're improving the retention time the way we wanted to. Or we can look at different plumbing and short-circuiting issues. Like with some of the different designs that we did test on, we can see, is the retention time lower because of this? There's a lot of different factors at play, but that could be one of them. And the tracer test helps give us some insight into this and helps us to compare OLB designs directly to each other by normalizing the data from these tracer tests. But all of them are useful tools and really helped us in our project, but more in trying to figure out, is there a better way to design these systems to achieve the desired results and help us see what is impacting the effectiveness of the treatment from the OLBs. So, thank you. And do you guys have any questions?
If cleaning the stone becomes a maintenance option, like based on the fact that you've done so many different systems, is it something you're like, okay, you should do this every 4 years no matter what, or you just do it when it starts to clog, or did you see any benefit by maybe doing it more often, or is it just no matter, it's dirty and then it's clean, so it doesn't matter necessarily when you do it?
Do the cleaning activity or to do these tests?
The cleaning activity. So like if you were going to, you just recommend, I don't know, but like are you saying in general, or what you've seen would be like, okay, it would be really good if you did this every 5 years, you get the most benefit out of cleaning that stone. Or, and I know in a lot of these cases, they're often forgotten or there's not a lot of maintenance, so
right.
It's just one of those things that it's just usually done when something's not working.
Right.
But if there was a preference or you consider it part of the maintenance, or you can make recommendations to a group, have you guys discussed that at all, or thought about what that might look like? I kind of got an answer, Olivia?
Well, yeah, I mean, just from my perspective, I feel like you have to kind of keep on top of the systems. And I know a lot of times some of the groups don't have the resources to do that, but once you see that it isn't performing as well as you'd want, or there's a decline in metal removal or alkalinity, then I would feel the discussion needs to begin, not when the bed has actually failed in doing it. But I'm sure Neil has some input on that.
Well, that's a good answer. The only thing I would add is that most of the fouling happens up front, like near the influent. So you got a 10,000 ton bed, you don't have to clean 10,000 tons. You're better off cleaning 2,000 at the beginning more often than cleaning a whole bunch of stone at the beginning. So it's not as big a task as it looks when you first see it. Focus on what's actually fouling.
And I'm going to speak since I'm in the same group, but also I think monitoring the alkalinity discharge and having in your mind when does it trigger concentration. We don't see the alkalinity generation go from 50 to 0 in 2 weeks. But in most of these cases, the starting alkalinity concentrations are say 120, 150, and when it gets down in the 60s or 70s, I personally think we have to do something. So I think that's an important thing to have a trigger idea. The other thing that has become an indication, you have sites that have manganese. Like on manganese, these beds remove all the manganese for a while. And the manganese removal is what degrades first. So that if you're that deep, you get out into the weeds, and now people watch manganese removal, not over the
I have two questions. So is that trommel, like the equipment, is that something that you can get very many places, or just like get used services of contractors? Is that a common piece of equipment?
No, to my knowledge, is not a very common piece of equipment. I think there's, yeah. Yeah. Yeah.
DJ contracting.
So just looking at some of your graphs, did you guys find that just the kind of the simple mixing and rinsing method was pretty effective at cleaning, you know, the metals?
Yeah, I mean, generally, it's really hard with the tests we did to like get at which cleaning method is actually better as far as metal removal or such and such. They all did a pretty good job of cleaning the beds themselves. So that's why it kind of then comes down to the unit cost and the throughput, because I would say generally, and correct me if I'm wrong, but the cleaning methods themselves chemically worked as far as improving the performance of the bed.
But that one site that you showed that had much lower porosity at the bottom as we went up in depth, we cleaned that with the dozer method. And so there we didn't remove, I mean, some of the solids came out the effluent, like the coke, but a lot of the solids got left behind, and apparently, per the data, got settled to the bottom of the bed, whereas the ones on the top were properly cleaned.
Yeah.
You can interpret that differently.
So, you're saying, are you saying that it's better off to clean 20% of the bed 5 times compared to cleaning it all once?
Oh yeah. Like you do have breakdown in the stone when you handle it every time, so you're gonna lose some doing that. But look at what's foul. I mean, the back end of the bed is almost always in good shape. So there's no sense in going through the motions of cleaning stone that's already clean. So
I'm just looking at it from the idea of if we have to stop the system and disturb the pond 5 times,
yeah.
Or do we stop it once for a little bit longer and do the whole thing?
Oh well, I don't think there's a whole lot of benefit in cleaning stone that isn't really foul.
What I'm saying is, if it's a pond that you're draining one end from the other, so it's going to foul across.
Yeah.
You wait till you're 3/4 or 80% fouled and then clean all of that.
Well,
as compared to doing 20%.
I think what you'll find is that the effluent quality will start to degrade before you're all the way across. Like you're going to need to do it from a treatment quality.
That's the quality of the water.
Yeah. Your outfall is going to tell you got to do it before it's fouled all the way across.
But you guys want a schedule, and so do we. But we don't know what that is.
Every
We
system.
don't know what that schedule is. What's the best thing to do? We just have data to start to assess.
And we have last question.
question, but so on slide 10, something that mattered to me when I had to do a similar project, I'm talking about cleaning stone.
Mhm.
You should add another column, or at least consider it, about what the replacement cost of stone would be. So, and I know it varies very greatly across the state, depending on your location, to a quarry. But maybe for each site, you could be like, okay, it costs us, the normal 20-ish some dollars a ton, or no, hey, we're really far, so this one would cost us like $54 a ton, or whatever it is. But to see the difference between cleaning and replacing or buying new,
Mhm.
and that became a problem for one of my sites because it wasn't that we couldn't necessarily get the money to do it to replace it, but my road had degraded over a 10-year period so poorly that I would have to put another $100,000 in the road to get back to the site. So that's why I did cleaning 10, 15 years ago, and we just did the hose and the bucket. But so that might help other people as you're comparing this data to kind of have what replacement cost that still might look like
Mhm.
as opposed to cleaning. So, because you're like, oh, that cost is 3 times larger than just using a hose or whatever, a trash pump and a 3-inch hose. But it's still significantly cheaper
Yeah.
than bringing in new stone.
Mhm. Yeah, that's a
And I
good
think
point.
these numbers are the stone, this is the full cost of the stone divided by the tonnage.
Yeah.
Whereas even just say, okay, $50 a ton to get a ton of stone, but you haven't gotten the stone out yet. So now you gotta add in the cost to get the stone out, and now you gotta put in the new stone, so it's even higher cost, it's more than just the replacement cost, it's the replacement cost.
What do you do with the old stuff?
Put it on the road.
Yeah,
Put
put
it
on
on
the
the
road.
road.
All right, that's all the time that we have for today. Thanks for sticking around. Our last presentation will be over in the ballroom, and that starts in a few minutes here at 3:30. Thank you, Olivia, and